we realize that as the body moves circular motion, we also see the body doing simple harmonic motion around O, up, down, down, up, and it repeats up, down, down, up. That continuously while the body embarks in circular motion. And so we got the displacement of the body around O at any time t by taking sine of omega t, which is equal to opposite. The opposite is y we are looking for. Y over, now r is also equal to a. When the body is doing circular motion, this distance is called radius. When the body is doing simple harmonic motion from here to here, we call it as amplitude. From here to here is another amplitude. But in reality, from this point to this point is the same as from here to here. We can say that they are all equal to the radius of the circle. And so r is equal to a. If r is equal to a, then sine omega t will be y over either a or r. Therefore, when we make y the subject, we have a sine omega t. And this equation is the displacement equation. Displacement equation of a body in simple harmonic motion. So if you want to get how an oscillating body is displaced with any time t, this is the equation. A displacement at any time t is equal to y is equal to a sine omega t. Now, class, when the body is oscillating and it's just at the center, it's like when the body is this, a simple pendulum, and the pendulum bob is just at the fixed point or the origin or the equilibrium position. What is its displacement y? At this position of the bob, what is its displacement y? Yes. At this position of the bob, what is the body's displacement y? Yes.
0.
Deborah, come again.
Please, I think it's 0.
It's 0. Because it hasn't moved. Displacement is any distance from the origin to any position. But if it's like this, it's just here. Its displacement is equal to 0. In the same way, when the body, oscillating body, is just here, its displacement is equal to 0. Now, when it comes here, it oscillates and comes to this point at one extreme. What is its displacement? When the oscillating body comes to this point, what is its displacement? Yes?
0.
Pardon? Pardon? When it's here, what is its displacement?
0.
Displacement is 0 at the origin. Oh. When it's here, when it's at this point and at this point, what is the displacement? Try. 0 is at the origin. At the extremes, what's the displacement? Yes. Deborah, try.
Mr. Edu, sorry, Mr. Edu, please. I think when it's at the extreme, the displacement is equal to like the radius.
It's equal to the amplitude. The amplitude is the maximum displacement. Okay, Mary, when I ask questions, I expect feedbacks from all of you. And there's no harm in trying and getting it wrong. Take note. Okay, so at the extremes, the displacement is equal to the amplitude. All right. So over here, the displacement is equal to A. Over here, the displacement. Now we can use the displacement equation to prove that. To calculate displacement at any point. And this is it. When the body starts at t is equal to 0, over here, this is a quarter of the period. Time is t over 4. This is half of the period. And this point is 3/4 of the period. And when it comes back, it is equal to t. So one complete oscillation, the time for it is the period. Are we okay? Now, when the body is just here, t is equal to 0. It's just starting. If you use the displacement equation, y is equal to a sine omega t, you can prove that the displacement at this point is 0 when it's just starting. Because y is equal to a sine. What is omega in terms of angular? Well, let me give that to you. Omega is equal to 2 pi over t. We proved this relation in our last meeting. So we have omega, which is equal to 2 pi on t times, we are here, or this point. So t is equal to 0, 0. When you multiply, this is 0. So we have a sine 0. Sine 0 is 0. And so y is equal to 0. So at the time t is equal to 0, y is equal to 0. When the body moves from here to this point, or from here, circular motion, from here to here, the time is equal to, t is equal to period over 4, quarter of the period. So if you are looking for the displacement of the body here, using y is equal to a sine omega, t is equal to period over 4. Now, omega is this. So when we substitute that into it, we have sine 2 pi over period times t over 4. This and this. 2 goes into this 2. So we have a sine pi over 2. What is pi over 2 in degree? What is pi over 2 in degree?
One eight.
What is pi over 2? Come again.
90 degrees.
That's 90. Because 2 pi is equal to 360. So pi is equal to 180. Therefore, pi over 2 is 90. So this is a sine 90, and sine 90 is equal to 1. So y is equal to a. Telling you that if the body moves to this point, time is pi over 4, and the displacement is equal to the amplitude. Yes, y is equal to amplitude over here. When the body moves from this point and then comes back, okay, here, what is the displacement? Over here, displacement will be equal to 0 because it has come back to the origin. Okay, so we are not going to calculate that. Then when it moves from here to this point, what is the displacement? When it moves from here and then comes back, what's the displacement? Mary. When it moves from here and then back to this other extreme, what is the displacement? Eliana, Mary, you will contribute. The body has moved from here to this point. What is the displacement?
Please, I think it's the amplitude.
It's the amplitude, but here it will be negative. When it comes here, the amplitude is equal to negative A. And we can use, is the negative of the amplitude. We can use the displacement equation to verify. And there's it. This is how to do that. When it's come back, the time, so we have moved from here to this point to this point. So over here, it has come to, the time here is t is equal to 3/4 of the period. When we put that into the displacement equation, we have A sine omega is 2 pi on t. The time is this. The time is 3/4 of the period. So this and this will cancel. This and this will cancel. So we have A sine of 3 pi on 2. Now, what is 3 pi on 2? What is 3 pi on 2 in degree?
270 degrees.
270. So the sine of 270 is equal to -1. Therefore, displacement y is equal to negative A. So Eliana, confirming what I said, when it comes back, the displacement is equal to negative A, negative of the amplitude. Then when it comes back again, displacement is 0. So we can plot this equation, the displacement equation of an oscillating particle over one cycle. And this is how to do it. That's exactly what we've done. So you can be asked to plot the displacement equation of an oscillating body over a cycle, over one cycle. And this is how that's how to do it. So this is why displacement here is against time. We consider different times. T. Our time we've divided into 4 quadrants. Our time t is equal to 0 is here. Then t is equal to t on 4. T is equal to half the period. T is equal to 3/4 of the period. And t is equal to the full period. That's it. So this is 3/4 t. This is half t. Oh, sorry, this is 1/4, rather. 1/4. This is 3/4 of the period, and this is it. So we are looking at the displacement of the body over one cycle. We have a positive amplitude. Let's assume there's the amplitude. So this is A. Then this is negative A. This is negative A. Now, just as we looked at, when t is equal to 0, what is y? At t is equal to 0, what did we get for y?
Y is
Yes.
equal to 0.
Y is equal to 0. So at t is equal to 0 here, and displacement is equal to 0. So there's it. There's the point. Now at t, I'm coming. So at t is equal to quarter of the period, what did we get for displacement? At t is equal to quarter of this, what did we get for
Y
y?
is equal to amplitude.
Good. So
Y is equal to amplitude.
good. So this time goes with, oh, the amplitude is too huge. Let me reduce it. So maybe somewhere here. So y is equal to a, which is here. Now at t is equal to half of the period. What is equal to, y is equal to what? At t is equal to half of the period. What is equal to the value of y? Yes. What did we get for y at t is equal to half of the period?
Pi.
Eh? We just did this. At t is equal to half of the
180.
period. What did we get for y?
Oh. It's really A sine 180.
I just did this with you. You were not watching. At t, we did this.
Y is equal to 0.
Y is equal to 0. So at t is equal to half of t, we got the displacement to be 0. So at this time, we have this. Y is 0 here. At t is equal to 3/4 of the period, what did we get for y?
Minus
Minus a. So at this time, it goes with a displacement of negative a. Then at t is equal to the period, capital T, what did we get for y? What did we get for y at t is equal to the period?
Mr. Adria,
I'm listening.
please, a bit lost.
You just joined us.
No, a few minutes ago, but still.
I'm coming. What did we get for, at time t is equal to the period, what did we get for displacement? Deborah and Co, I'm waiting for you. We did this together. At t is equal to the period, what did we get for y? Nobody is talking.
0.
So we got displacement of 0. If you don't stop this attitude, in fact, we will close lessons. If I'm doing this and you won't pay attention to contribute, expecting that I tell you everything, we'll close the lesson. So you better pay attention. I did this with you. So at t is equal to the period, we got a displacement of 0. So this time goes to the displacement of 0. Then when I finish, I'll go over. But when I'm doing it, pay attention.
Yes.
So when you finish, you just join your points. And this gives you the displacement equation of a body doing simple harmonic motion over one cycle. Over one cycle. Over one cycle, the body, when a body is doing circular motion, it is also doing simple harmonic motion. So when it goes, the body goes around the circle once. It is the same as starting from O, moving up, coming down, and moving back to where it started. And so this is the displacement equation for one cycle. I'm going over. Pay attention. Nanadua and Co. Mary, are you there? Mary. So last time we derived the displacement equation of a body doing simple harmonic motion as this. And you were here. We derived this. What this simply means is that this is the equation that displays how the body is displaced from the equilibrium position origin at any time t. So when it moves from here to here, from this point to this point to this point, and back, you can use this to find the value of the displacement. So we call this as the displacement equation with time t. So at any time t, you can be able to find how the oscillating body has been moved from the origin or how it is displaced. Okay? Is that okay?
Yes, please.
Now, we want to draw the displacement function for an oscillating body over one cycle. And one cycle is in circular motion is equal to moving round a circle once. In simple harmonic motion, one cycle is starting from the origin, getting to this point, coming back, and then so up, down, up, one cycle. So we want to draw the displacement with time, the displacement of the body with time. So that is what we are doing here. So as if we haven't done anything, I'm cleaning everything. Open your eyes and watch. So I draw a graph of displacement y against time t. Now, we are dividing the whole time into 4 parts. That is, when it moves from this point to this point, from here to here, from here to here, and from here to here. This is the same as when it is oscillating, moving from here to this point. This is 1. 2, 3, and then 4. Are you okay? Nanadwa and Ko, are you okay?
Yes.
Yes, please.
So the time is divided into when t is equal to 0 is here. When t is equal to quarter of the period, so 1/4 of the period, then half of the period, then 3/4 of the period, then the full period. So we have this as 1/4 of the period t. We have this point as half of the period t, and then 3/4 of the period t, and then the full period t. So if you can see, we have divided this into 1, 2, 3, 4, the time into 4 parts. Now, when it oscillates from this point to this point, this is the amplitude, which is the maximum displacement. So we must have a column for the maximum displacement A. So this is A. And when it moves from here to here, there's another maximum displacement, but it is to the negative. So we have this side also as minus A. Maximum displacement here, maximum displacement here. Okay. Now we are going to calculate for the displacement. At t is equal to 0, what is the displacement? And this is what we are going to use. When t is equal to 0, y will be equal to a sine omega t is 0. So this t is 0 times 0. However, we know omega to be equal to 2 pi over t. So when you substitute omega into, we have y is equal to a sine 2 pi over t times 0. And this part gives us 0. So we have a sine of 0. And what is sine 0? What is sine 0?
0.
So this is 0. It means that at t is equal to 0, the displacement is equal to 0. So come and plot it on the graph here. This is y is equal to 0. It starts from the origin. At t is equal to quarter of the period, the displacement y is equal to a sine 2 pi on t times the time t is quarter of t. So calculate the displacement for me. I've substituted values. Calculate y for me.
Y is equal to A.
So y is equal to A. So you come to the time at t is equal to 0, the displacement is equal to A. So you link the graph, the time, the graph thing y is equal to A is here. So this is it. Then you plot. Okay, calculate this for me. At t is equal to half of t, what is y? Yes. Do that and then tell me what y is. At half of the period, what will be the displacement y?
Mr. Dear,
Hello?
so I don't understand why when t is equal to quarter of the full period t, y is equal to A.
We are dividing this quadrant. You said you don't understand when
small t is equal to quarter of capital T, why is y equal to A?
Okay, so
Like how is y equal to A?
t would cancel out. Then 2 goes into this 2. So you have a sine of Now again, what is left? T has cancelled. 2 goes into 4, 2. So what is left here?
Half pi.
Half pi or pi on 2. Pi on 2 is an angular measurement in, I'm coming. It's an angular measurement in radian. The equivalence of half pi or pi on 2 in degree is 90. Now, are you there?
Please
Yes.
come again.
So, pi on 2 in degree is equal to 90 degrees. And this, we learned it. So, some of you, you know. Those of you who couldn't join us, fine. But pi on 2 is equal to 90. If pi on 2 is equal to 90, then you have a sine 90. And again, for what is sine 90?
1.
So that's why, so you are a times 1. And y is
Yes.
equal to a.
Thank you.
Okay. So at half, at t is equal to half period, y will be equal to what?
0.
0. Good. So when you plot that, you have t is equal to half, plot the corresponding y, 0. Now calculate this for me. At t is equal to 3/4 of the period, what will be y? Calculate it for me. Nana, do I calculate? And those of you just join us.
Negative A.
Good. So y will be equal to negative a. If y is equal to negative a, then plot it. At t is equal to this, what is y? Negative a will be somewhere here. So I must clear this.
Miss Peja, please, how did you get negative A?
Ask mommy Nana, Nana Joa, I ask you to pay attention. What's the name? Nanefua, how did you get negative A? Tell her.
Mr. Edia, you see,
Nana Joa, are you listening?
you said the displacement equation with time t is a sine omega t, and since omega is equal to 2 pi on t, you put it into the equation, and the time t is equal to 3 on 4 t.
So Nana Joa, that's it. Omega is equal to 2 pi on t. Then the period, the time is 3/4 of the period. T is equal to this. So if you substitute, we substituted the value of omega. And so t, 2 goes into this. So you have sine of 3 pi on 2. And another, what is 3 pi on 2? Nanadua,
Mr. Adrian,
what is 3 pi on 2? This angle is in radian. What is its equivalence in degree? There's somebody to tell her.
Mr. Adria,
Yes.
since pi is equal to 180, then 3 times 180 will give you 540, and you divide it by 2.
And that will be
270.
So
And
it's this.
sine of mm,
Go ahead. Go ahead.
and sine of 270 will give you negative 1.
1. So Nanadwa, this is the same as a times negative 1. What is that? What is a times negative 1?
Negative A.
Okay, so that's why this time gives us a displacement of negative a. Okay, now Nana Jemfua, calculate at t is equal to period. What will be the displacement? Nana Jemfua, over to you.
Please, the displacement is 0.
Is it by Lotto?
Oh, no, please, I've worked it out.
Janice, are you following?
Yes, please.
Okay, so displacement is 0 here. Now when you plot, just now plot your or join your points. And this is the displacement equation for an oscillating body over one cycle. So if you are asked to plot a displacement equation for an oscillating body over one cycle, this is it. And there has been questions on something like this before. I have the question. I'll just throw it to you and you will see. So pay attention to this thing. Now, the term simple harmonic motion. Can I clean this? Can I clean it?
Yes, please.
The word simple harmonic motion, each and every term has its meaning. Simple harmonic motion. The word simple means this motion occurs at a simple or constant simple angular speed or velocity. Simple or constant angular speed or angular velocity. I told you that every oscillating body occurs at a constant angular velocity, omega. So that is the part of it, that part of it is what this describes, simple. The word harmonic in physics means that repetitive or repeated. A harmonic function is a repeated function. It's a function that repeats. Why does it repeat? Sine functions, cosine functions, we call them as harmonic functions because they repeat. Now, assuming we want to continue over one cycle or over two cycles, what we've drawn is for over one cycle. Assuming we want to do it over two cycles, see what happens. So let me reduce this thing small. Can I clean it?
Yes,
Can I
please.
clean it? So let me draw circular motion. We'll draw it over two cycles. We do it with a circle because any circular motion produces simple harmonic motion. So this is Y. This is T. Now over one cycle, look at it. It starts from T is equal to 0 over here. And when it's here, quarter of the period. When it comes here, half of the period. When it comes here, 3/4 of the period. When it comes back to where it started, we have the period. Now we are going to start again. Okay, so 1/4 plus 1/4 plus T. We have added here. So we are adding 1/4 to it plus T. What will be? What is half quarter plus 1? Yes, quickly calculate that for me. Quarter plus 1.
Five over 4.
So this is 5 over 4. 5 on 4 T. 5 on 4 plus another quarter. Every half is quarter. So 5 on 4 plus another quarter.
3
Meaning
on
we are
2.
what?
3 on 2.
So 3 on 2. We are here. So 3 on 2 plus quarter. 3 on 2 plus quarter.
7 on 4.
Elder, speak out.
7 on 4.
7 on 4.
Yes, please.
You are talking as if you are tired. Then when we come back from here to here, 7 on 4 plus quarter.
2.
This is 2 period. So we are taking this function over 2 periods. It's like 1, another 2. Okay, which is the same as moving from here to here, coming down, and coming back again. Okay, from here to here, here, 1, here, 2. That's what is happening. Good. So we realize that when at t is equal to 0, the displacement is equal to 0. Okay, let's have our amplitude here. A is here. A is here. Then minus A is also here. So in the first cycle we've drawn, there's it. When t is equal to 0, there's it. When t is equal to quarter of the period, y is equal to A. So we have this. At t is equal to half of period, y is 0. At t is equal to 3/4 of the period, y is equal to minus A. Eliana, are you there? At t is equal to
Yes.
4 period, y is equal to A. No, y is equal to 0. And so we came here. Now do this for me. Find the displacement for t is equal to 5 on 4t. Adelaide, no, Janice, do this for me. This is for Janice. Now, T is equal to 3/4 of the period. Mary Clark. Mary, are you there?
Yes, please.
Well, what is your own casa? Yes, please. Your voice, I hear yes, please. Yes, please.
Of
Hilda, yours is T is calculate the displacement for T is equal to 7/4. Hilda. Then let me search for somebody. Somebody who wants to be quiet on the platform. Nanajua. Nanajua at T is equal to 2 capital T. What's the displacement? Calculate and tell me. Janice, are you through with yours?
Yes, please.
What did you get? At T is equal to 5/4 of the period.
3/2.
Y is equal to
3/2.
no. Look at it again. Look at it again. Y at T is equal to 5/4 of T. What is Y? Deborah, confirm with Janice. Deborah, calculate 2.
Which one? The T is equal to 5/4.
Yeah, 5/4. What will be the period?
I
Collaborate
got
with.
the displacement was A.
The displacement is what?
Was A.
Was equal to the amplitude. Yes.
Yes.
Janice, it will be equal to the amplitude because we are talking of Y is equal to A sine omega is 2 pi on T. That time is 5/4 of the period. So this and this, this and this. So we have A sine 5 pi on 2. And what is 5 pi on 2 in degree?
450.
And what is sine 450?
1.
1. Okay, so Janice, this is A sine 450 in degrees, and sine 450 is equal to 1. Therefore, the displacement will be equal to 1. Janice, are you okay?
Yes, please.
So we trace the displacement to the time. Nobody will be quiet. So this is it. This is our point. The positive seems to be taller than the negative. Okay, Mary. That was the displacement at time 3/2 of the period.
the displacement is 0.
The what?
The displacement is 0.
Yes, the displacement is 0. So this time goes with displacement of 0. Hilda, the displacement at the time 7/4 of the period.
Mr. Chair, please, it's minus A.
Code minus A. Kanadua, displacement
Why is
at
called 0?
then are not the why is 0? So look at something. When we join, this is it. Now, you realize that right after one cycle, all that we had for the displacement with the time is repetitive. Okay, look at it. At this time, displacement is 0. At this time, displacement is A. Displacement is 0, displacement negative A, and then 0. Then after one cycle, it's the same thing repeats. Okay. At the time the displacement is this. 0 again is this. 0 again. If you continue, that is how it will be. So whatever you get after one cycle repeats. Repetitive. That is why we call the motion harmonic. All harmonic motions are repetitive motions. If I ask you to draw it for 3 cycles, 4 cycles, you realize that it will be a repetition of the first one. Hence, simple harmonic motion. So for a simple harmonic motion, it is a motion that occurs at a uniform or simple angular velocity, omega. And the motion is repetitive. And we've just demonstrated it. So if you are given any function, a sine function or cosine function, it means a sine function and a cosine function are harmonic functions. They repeat after one cycle. Please, all is well. Do we understand?
Yes, please.
All right. Now, so this is the displacement. Okay. Now, once we see the body oscillating, moving up and down about O, the origin O, if we are near Naba, it means its position or displacement is changing with time. And if you have a body whose displacement changes with time, what does it result in? Or what does it amount to? If you have a body whose displacement varies with time, what does it produce? Yes. Come again.
Acceleration.
It's not true. When the body's displacement changes with time, when a body's displacement changes with time, what does it produce?
Mr. Edia,
Mm-hmm.
I'm not sure.
Be sure. Be sure and then when the body's displacement changes with time, what does it produce?
Velocity.
Velocity. Deborah, I have to beat you. Okay. So, because the body's displacement changes with time, at another point it is here, at another point it is here, another point it is here, up and down, okay? It means that it will have a certain velocity because the rate of change of displacement with time gives us velocity. So because the displacement of the body changes with time, we have to find the velocity function of an oscillating body, a body doing simple harmonic motion. So why are we looking for the velocity function? It is because the body's displacement changes with time. At another point, it's up here. It's at the amplitude. At another point, its displacement is 0. At another point, it's increasing, and then gets to the amplitude. Another time, it is decreasing, 0. So when we have displacement changes with with time. Nanajua, it amounts to what? Nanajua, it amounts to. Nanajua won't mind me. She will come back and then tell me, say, I don't understand. Okay. But I'm sure after taking you through this, when they ask you to draw the displacement graph for 5 cycles, please, can't you do that? For 5 cycles, can't you do it?
We can.
So easy. So easy. So you draw 5 cycles for me. Now, because velocity is equal to the y on the t, the rate of change of displacement with time. If we want this velocity function of this body, it means we need to differentiate the displacement y with time. So we substitute the displacement function a sine omega t into it to obtain the velocity function. Please, before we continue, you see the same graph can be drawn using angles. Don't forget, at t is equal to quarter of the period. It's when the body moves from here to here or from here to here. And the time over here, the angle over here is equal to 90 degrees. The angle over here is equal to 180. The angle over here is equal to 270. The angle over here is 360. And then starting from 0. So this same thing can be drawn in terms of angles. When t is 0, this is 90, 180, 270, 360, then plus 90, 360 plus 90, plus 90, on and on. So note that this same function can be drawn in terms of angles. We did that in terms of time. But when you are doing it in terms of angles, you have to use y is equal to a sine theta. Don't forget I said theta is equal to omega t. So when we substitute omega t for theta, this is what we had. But when we are writing the displacement or drawing the graph, the displacement function with angles, this is what you use. Please, are you okay?
Yes, please.
All right. All right. So because velocity is the rate of change of displacement with time, that's it. Now, you haven't done differentiation, I know, but we are going to apply differentiation in elective maths. Okay, but before that, I think I have to introduce you a little bit to it. Have you done differentiation?
Yes, please.
Where?
At home. Online.
No. Okay. So I'm taking you through differentiation of trig functions. Maybe linear equation, then I apply to trig function quickly. Differentiation, we are looking at how one variable changes with respect to another. So the differential of one variable with respect to another variable. And so here we are looking at how displacement changes with time. And we know when displacement changes with time, it gives it amounts to velocity. So how displacement is changing with, so if you have a function, what, and then the function is related to another function by this. Maybe y relates to n, x by this, where N is a power. And you are asked to find how y changes with respect to time, with respect to x. Mathematically, we express that as dy by dx. How y is changing with respect to x. And dy by dx is equal to, now this is the formula. In differentiation, when we are differentiating, the power multiplies the whole function x. And then this power at every differential reduces by 1. So n minus 1. If I have to differentiate this again, this is a first differential. If I need second differential, then del dx of this one, dy on dx. And this will give us the squared y over the x squared, meaning I'm differentiating twice, but I'll differentiate this and I'll differentiate the same thing again. And that's what we call as the second differential. The second differential, which is the squared y of the x squared, is equal to, at every stage, the power multiplies it and that same power reduces by 1. So n minus 1 times n, then x raised to the power n minus 1, which is equal to minus 2. So generally, if I have to differentiate, if I have to differentiate y with respect to x, which we call as dy by dx, this is equal to the power times x, then this power reduces by 1, n minus 1. This is what we call as differentiation. So example, if I have y is equal to x raised to the power 5, and I'm asked to differentiate, dy on dx will be equal to 5 times x, then the power reduces by 1, 5 minus 1, which is 5x to the power 4. This is the differentiation of a common function, a linear function. Now what we are going to do is about trigonometry. So what about the differential of trig function? If I have y is equal to sine theta, here I'm differentiating y with respect to theta, the angle. So dy by the theta. And this is a rule. Whenever you differentiate a sine, it is equal to, the differential of a sine function is equal to a cosine function. The differential of a sine function, put that down. The differential of a sine function is equal to a cosine function. So dy on the theta, the y is equal to sine theta. The dy on the theta will be equal to, okay, if this is x, if what we have here is x, then the angle is x. So the differential becomes dy on the x is equal to cos of x. It's a formula. Now, if you have y is equal to cos x, a cosine function, and you have to differentiate, the differential of a cosine function, the y angle is x, the x is equal to a negative of sine. So whenever you differentiate a cosine function, it's equal to the negative of a sine of its sine function. So put these two down. This is what we are going to apply, because what we have is a trig function. Please, are we okay? Are we okay?
Yes.
All right. So to get the velocity function, I have to differentiate this function. So del dt of a sine omega t. Okay. Now, earlier, okay, let me do that. Now, another thing you must understand is that if I have the sine of x, the differential of sine x is equal to dy dx is straight away equal to cos x. But if you have y is equal to 2, maybe 3 sine 2x, we call this a function of a function, one function in another function. This is a constant or a coefficient. The coefficient is never affected in a differential, so it will always remain. Okay, a coefficient always is repeated in a differential. It will never be affected. So, but you see, we had only x, but over here we have 2x, meaning we have one function 2x in another function sine. Okay, so we call this a function of a function. If you have a function of a function, you differentiate the function first, the daughter function, this is the daughter. Then you come and differentiate the whole mother, which is sine 2x. So it's a rule. Okay, let's apply the rule and then you follow. I know you haven't done it, but we need to apply it in physics. So assuming we are to differentiate this, dy of the x will be equal to 3 will never be affected. So it comes out. Now, because this is a function of a function, I have to find the differential of this function, daughter function 2x, times the differential of the mother function del dx of the mother sine 2x. This is how it's going to be. So 3, which is the coefficient, which is unaffected, but the differential of 2x is equal to 2, because when this is equal to 2 out, the x on the x, this and this will cancel, times when you differentiate sine, it is equal to cosine. So this is times cos of 2x. And so in effect, this differential will be 3 out 2 cos 2x, which will give us 6 cos 2x. Okay. As we'll be applying it, please, you master. Don't let it scare you. I know because you haven't done it, it will scare you a bit, but don't let it scare you. So all that we have to differentiate is this. We are differentiating the displacement function. Okay, let's apply the rule we just learned. This is a coefficient. It will never be affected. So it comes out, but we have the differential of sine omega t. Now, a out. This is also a function of a function. So we differentiate omega t del omega t of dt times, when you differentiate sine, it is equal to cosine cos omega t. So you have a out. Now, the differential of this will be equal to omega, because here we have omega out dt over dt. So dt will cancel out, remaining omega times cos omega t. When we apply it, we have A omega cos omega t. And this is the velocity function of a body doing simple harmonic motion. The velocity function of a body doing simple harmonic motion. Please, are you okay? Are we fine?
Yes, please.
Or everybody is asleep?
Miss Lydia,
Hello, Anna.
why have you written the W twice? Can't we like put together? We can't put together.
No, this is, you see, this is a function in one function.
Mm.
Okay. So this thing is, okay, is similar to a fetus in the belly of a mom, okay? So you cannot, yes, the rule is that because it's a function of a function, you have to differentiate omega t with respect to time. And that gave us omega. Okay, but the daughter or the fetus within it must be repeated because you once again differentiate sine omega t to give you cos omega t. So the fact that omega is here does not mean you can multiply. No. Okay. It's a function of a function. You saw it coming out because we had to take omega t alone, differentiate with time, and we got omega. But the differential of sine omega t would overall give us cos omega t. That's why this is repeated. All right. All right.
Yes.
Now, therefore,
Yes, Mr.
everybody is
Oh,
asleep.
Mr. Edia, no.
That is Hilda. You come out of the hills. Ileana. Eliana has covered herself with a cloth. That Deborah has gone to see the Deborah in the Bible. Jan is the original. So this
Hey,
is
Mr. Edia.
hello. Ask questions. The questions will help you understand. Hilda, are you there?
Yes, please.
Okay, so we call this as a velocity function of a body in simple harmonic motion with time. Actually, this velocity function is in terms of time. Let's see how we can also apply that. When a body is doing simple harmonic motion, Deborah, where do we have the maximum velocity? Where does the maximum velocity occur? Deborah. Oh, I said it. She's gone. Where does the maximum velocity of an oscillating body occur? Where does it occur?
Adam, please.
Maximum velocity.
No, like the farthest place they will go.
I said velocity. Where does the maximum velocity occur? Yes.
At the
Mary.
equilibrium.
Mary. Mary. Yeah, Eliana. Eliana. Hey. So they will even mind me.
Mr. Adria.
Hey. After calling you that number of times, where does the maximum velocity occur in an oscillating body or a body doing SHM? Where does the maximum velocity occur? Hilda.
Mr. please, I'm thinking about it.
Janice, where does the maximum velocity occur? And where does the minimum velocity occur? Nanadua, you were in class when we treated this. You were right here.
Mr. Edia.
Yes, please.
And Nana, if what?
Does it occur at a fixed point?
The maximum velocity.
Yeah, or when there is no displacement.
Yes. So the maximum velocity occur at the mean point or at the equilibrium position. So when the body is moving, as at when it is about to cross this point, we call at the mean point, it crosses it with the maximum velocity. So we say the maximum velocity occurs at the mean point. The minimum velocity occurs at the extremes, at the amplitude. That is why if a body is oscillating, simple pendulum, when it comes here, whenever it comes here, it stops and would have to return. It gets here, it has to stop and come back. When it gets here, it has to stop and come back. So the body does this simple pendulum, oscillating around it. So at the extremes, at the amplitude, the velocity is zero. Velocity is zero here at the extreme. Now, velocity is maximum at the mean point. So V is maximum. Are we okay? Are we okay? Are you fine?
Yes, please.
My bra yampon wati. My bra yampon. Sakasa yamudian, let's close and go. So let's see. This body is oscillating. V is zero here. V is zero here. V inverse. Let's see. The formula. The formula will tell us we had the velocity of a body doing simple harmonic motion as A omega cos omega t. This is what we had as the velocity function. Now, what is the velocity when at the time t is equal to 0? When the body is here, what is its velocity? Yes, we've learned, this is what we've learned. We've learned that omega is equal to 2 pi on t. So substitute t value omega and then tell me what you have for velocity at t is equal to 0. Then, so Nana Jamfua, this is for you. At t is equal to a quarter of the period over here. When it comes here, 1/4 of the period, what will be V? Eliana, this is yours. Nanadwa, at t is equal to 3/4 of t. What is the velocity? Then Nana Jemfua, at t is equal to the period, what will be V? Do that for me. So Nanadwa, Nana Jemfua, Eliana, okay, Eliana, this is yours. Hilda, this is yours. Do it and tell the rest of you must also do it. At least we are all learning. Yes, Hilda, what did you get for V at t is equal to 0?
Miss Teacher, I got V is equal to 2a pi on t.
2a pi on t.
Yes, please.
You forgot to convert the angle from radian to degree. That's why you still have t there. So V is equal to a omega cos 2 pi on t, just as we did here. 2 pi on t times t is equal to 0, so 0. All this part goes to 0. So you have a omega cos 0. And what is cos 0? What is cos 0?
1.
That's 1. So you have b is equal to a omega. Yes. So this expression tells us that at t is equal to 0, the velocity is equal to the amplitude times the constant angular velocity. So this becomes the amplitude. The whole of this becomes the maximum velocity. So when we finish, we'll plot it. Okay, so at t is equal to 0, velocity is this. Now, at t is equal to quarter of the period, the body is here, or having moved from here and it's here. Eliana, what did you get for V? When t is quarter of the period.
Yes, I got D is equal to A omega cos 90.
Cos what?
A omega. I got
You had V
about
is
0.
equal to A omega
Please.
cos 90, and cos 90 is 0.
0. Sorry.
So velocity is 0. What it means is that when the body oscillates and then comes to this point, the velocity is 0 here, which I told you. That's why V is 0. At the maximum displacement or at the extreme, velocity is 0. Okay, t is equal to 3/4 of the period. What's the velocity, Nanadua?
V is equal to 0.
When the body is here. So in circular motion, it's like having moved from here to this point. In simple harmonic motion, it's like moving from here and coming here. So over here, because we are at another extreme, velocity is 0. Okay. Nanejefua, what's the velocity when the time is equal to t?
V is equal to A omega.
So anytime the body crosses the mean position, its velocity is maximum. At the mean point, velocity is maximum. At the extremes, the velocity is 0. So food of thought that velocity of a body in simple harmonic motion is maximum when crossing the mean point, and it is 0 at the extremes or the amplitude. Let's plot a graph of velocity against time for an oscillating body. What we have had is graph of displacement against time. Say, "Muhumi, I'm begging me back." So, velocity against time. We've done it for displacement against time. So this time we break, this is V, this is T for one cycle. We are doing it for one cycle and you go and add on. So at quarter of the period for one cycle, at half of the period, three-quarters of the period, and then over a period, you would add on. Eliana, at t is equal to 0, what did we get for velocity?
A omega.
So it's equal to the amplitude. So let's indicate the amplitude to be here, A omega. The next amplitude is minus A omega. Good. So at t is equal to 0, velocity is maximum. What did we get for velocity at t is equal to quarter period or quarter part? Yes. Hilda, what did we get for velocity here? Hilda,
Mr. Ejia,
what did we get for velocity at t is equal to quarter of the period? You've forgotten. You calculated for it.
no,
What
I
did we?
calculated the t is equal to 0.
And Eliana, what did you get here?
0.
What's our DNA on casa? Nanajua, what did you get for the velocity here? What did we get for the velocity at t is equal to half of the period?
Mr. Ejia, please, I'm not done solving.
What did we get? Whoever solved this? T as,
We got 0.
wait, no, it wasn't 0.
Mr.
Because
Ejia,
half of it is here. And the same as moving here and then coming here. So it cannot be 0. This is quarter of the period.
Negative amplitude times. Yeah, what?
Mr. Ejia, we had Z.
We had what?
Z is equal to
Mr. Edia,
Speak, I'm listening. Hey, the animal calculation.
um,
The same thing we've calculated over and over. That what I why dean or show. As we have. And I'll send them my main chain. So phi is equal to A omega cos 2 pi t. The time is half of the period. We had, this is cos 180, and cos 180 is -1. And so the velocity is equal to negative of AW, of the amplitude. So at t is equal to that, we'll have this. We have the velocity equal to negative of the amplitude. We are here. Now, what's the velocity at 3/4 of the period? Yes.
Velocity is equal to 0.
Velocity is equal to 0. What's the velocity when t is equal to period? What's the velocity when t is equal to capital T, the period? If you've forgotten, calculate it and
A
stop being
omega.
quiet. A omega. So at the period over here, when the body goes and then comes back, it is at the rest position. So it's like moving from here, going here, coming here, and coming back. When it's coming back, its velocity is just maximum. So the velocity is A omega. So when you join, this is what you have. For one cycle. So this is the velocity function of a body doing simple harmonic motion over one cycle. Your assignment is that do it for 2 other cycles. So this is over one cycle. Over one cycle. Do it for 2 cycles, 2. And then a 3rd cycle. So all that you are doing is that you are adding quarter of the period to the time. So this will be t plus 1 on 4, whatever plus blah, 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 for the 2nd cycle and then the 3rd cycle. And then calculate to draw the velocity function for 2 other cycles for me. So you do it for 3 cycles. That is your assignment. Please, is that okay? Hello,
Mr.
is
Jack,
that?
is it for velocity?
Is that there?
This is it for the velocity only?
Yes, you are doing it for yes. You let me reserve it for velocity. You are writing the velocity function of a body doing simple harmonic motion for 3 cycles. I've done the first one for you. You are going to do the second one and then the 3rd one. The velocity function of a body, an oscillating body, for 3 cycles. That's your assignment, which you do it and send to me afterwards. If there's any question, ask. If there is any question, ask. If there is no question, then this is where I draw the curtains on our meeting today. In fact, today your responses have been woefully annoying. Annoying. It's as if you are at sea. Okay, but that notwithstanding, I will still expect the assignment from you. If there is the need for you to collaborate with among yourself to do it, do so until next week. In fact, bye-bye. Go and sleep. Have a sound sleep.
Bye. Good night.
Oh, Mami Nyame.